of the steel bar which will be used. Okay, so and it is going to be formed like this. This you can consider as two cantilevers. One cantilever on this side, another cantilever on this side, and Q by 2 acting here and Q by 2 acting here, and these two cantilevers will deform, and you can see that this deformed shape is same as this. You agree? Why? Because at the midspan the rotation is 0, so it is acting like a fixed point. So as if two cantilevers are fixed at the center. So can you plot this Q versus delta in this case? So let's use the elastoplastic relationship. It will be something like this, bilinear relationship which we have used. So Qy and the corresponding value delta y and delta u. And the value of Qu. So how much is Qy? If this section at the center is known, I can plot m-phi curve for this, and I can calculate my, phi y, mu and phi. So using these values of the section, okay, and this length, let us say L by 2. Can you calculate Qy and delta y? In this case, so how much will be Qy?
4 m by L. 4 m by L.
4 m by L. How did you calculate? This moment capacity here. This is m. Okay. So Q by 2 into L by 2 is equal to m by. So m by is 4 my by, sorry, Qy is 4 my by L. Can you tell me delta y? 5 by L square by 6. How? Q by 2. Okay. Sorry, 5 by 2 into L by 2 whole square by 3. It is cantilever. So here the curvature is phi y when yielding is occurring. Okay. So phi by 2, sorry, phi y into L by 2 whole square by 3. And it will not be multiplied by 2.
Yes.
In case of fixed beam, you have multiplied by 2. So is it L square by 6 or 12. Agree?
So pi y L square by 3 how equal? It should be pi L square, pi y L square by 3.
Okay, so our displacement is this. This is our delta. Okay, which is same as this. So this delta you are obtaining from this cantilever. Okay, so how much will be delta? If the curvature here is 5i, how much is delta? This is L by 2. So that will be 5i. Substitute this 5i to my over ei.
Pi over y is itself pi y.
Right. So 5i you substitute my over ei. And then my you substitute q1 and see what relationship you are getting in delta y and q1. Delta y in terms of q1 into what? L cube over. Is it a familiar relationship? Because still yielding the linear relationship is right. Now, how much will be delta U? Is calculation of delta you will figure? You have already done it for cantilever. delta y plus delta p, and delta p is theta p into LP. Okay. Sorry, delta p is theta p into L, and theta p is phi p into L. So how much will be this? So it is delta y plus delta t. Delta y you have already determined, so I will keep it as it is, plus theta p into L or L by 2. Is it okay? Everybody agrees with this? Anybody having doubt here?
Sir,
Yes.
it should be delta u plus theta p2
Sorry, it should be delta. Delta.
corresponding to ultimate load.
Uh-huh.
Yield displacement will be delta y.
Right.
We are making here delta y equal to corresponding to yield.
Yes. Delta y is yield which I have determined.
It should be delta u. Delta u elastic.
Delta u elastic. Delta u can't be elastic.
Corresponding to that qy changes to qu.
Qy changes to qu.
And
Right.
qu corresponding to that qu there will
So if you substitute qu here, will you get delta u? No, because relationship is not linear. Relationship is linear. This relationship is valid only up till yield.
no that delta u plus plastic deformation theta p into L by 2. Delta ultimate equal to delta u elastic plus theta p into L by 2.
What is delta u elastic?
Delta u elastic will be corresponding to qu load. That is this will be qu.
Suppose qu is higher than qy.
Qu that is
So can delta u elastic more than delta y?
no.
Okay. So delta y will remain delta y. Delta y is not going to change. Only thing is that this additional plastic rotation will add. And plastic rotation is theta p into length. Length I have written L by 2. So is there any problem with this? Why are you so silent? Some doubt in your mind? Or if I am asking, there will kuch to gadbad hoga. है ना? So if you have sensed the gadbad, tell me. Right, at the midpoint. So in what is going to happen here? If you look at the beam, so from the center, at the center the moment will be maximum. Yielding will start from here. Okay, and this length here and this length here is going to yield in both the directions. Okay, so length of this steel will yield, and this length in the center, this we are representing by L, the plastic film. Okay, it will be less. actual area which is plastified, you can see that this area is plastified on this side, this area is plastified on this side. Like if it was a steel beam, okay, so this much portion would have plastified. In concrete, it is not same, it's complex. Okay, concrete has different property than steel. So this much steel length is going to plastify, and accordingly we can calculate what length of the concrete has plastified. Concrete has got a strain more than 0.0015. That we will call plastified. Okay. So yes.
You are considering that separated beam in two cantilevers.
Yes.
And at the section where you are considering that beam, at the left hand side and the right hand side, both the mounts are equal.
Right.
So while considering LP, we should consider from the center to this side LP, this side LP. Not
So we should consider 2 times LP.
2 times LP. This side LP is because the two cantilevers are there. And moments are also equal at that sections where we are cutting.
So what will should we consider 2 times LP?
No sir, but data will be same because we are dividing the whole beam into 2 parts. So if we consider a single cantilever beam, so this much length, in the case of a single supported it is LP. But if we will divide the length, plasticide length in the cantilever,
Okay.
it will be LP by 2 simply.
Okay.
So that LP by 2 is LP in our case.
Now think about this. I have a beam here, and in this beam I provide a hinge in the middle. Okay, apply some load, it is going to rotate like this, like rigid body.
Yes.
Okay, how much is the rotation which is occurring at the hinge? Is it theta or 2 theta?
It is same theta.
It is theta.
The rotation at hinge.
It will depend also on the length of the both sides.
It is same as if I rotate this, let us say, I rotate the whole thing as a rigid body by angle theta, so that this becomes horizontal. Okay, and then this will be like this. How much will be this angle? So the rotation actually which is occurring at the hinge is not theta but 2 theta. Okay, it is to be measured between these two segments. Okay, so the angle which you are considering here, it has to be theta p by 2, not theta p, because the same theta p is contributing to rotation of both the sides. Okay, so the rotation which is occurring at the plastic hinge is double of this chord rotation. This is chord rotation. Okay, in our case, this is chord. If it is not deforming, it would be straight. If it was deforming, it would have been like this. But this is the chord rotation. Similarly here, this is the chord rotation. So the chord rotation is 2 times theta. So that's why here we are considering theta p by 2. Yes. 2 theta maximum. This figure you agree? This figure you agree? So it was like this. I have rotated it like this. So I made this portion after deformation horizontal. I can do that. There is a rigid body rotation. So I made a rigid body rotation. So if I am doing a rigid body rotation, I am not changing anything. The configuration remains same. So then you can see that this angle is 2 theta. Actual rotation which is occurring here is not theta but 2 theta.
So,
Yes.
how that support can go?
No. I am rotating. Suppose support has not gone. I have bent like this. Okay. Support is there itself, but I am seeing. I have taken photograph by rotating my camera. Then I can take it like this. Supports are still in the same line as here. But I have rotated the camera, let us say. If I'm not able to rotate the support.
Not getting. Not getting.
Not getting. Suppose this, let me draw it on paper. Can I get it on paper? Okay, I will draw it on your copy. So, this you understand?
Yes.
I have rotated it like this. Your copy I have rotated or you have rotated with respect to the copy. So what will happen? This is becoming horizontal now. So how much is this angle? 2 theta. The same thing is here. Actual rotation which is occurring at the hinge, okay, is 2 theta. Because both sides are rotating. So the angle is to be measured which is occurring between the two segments. Okay, not from horizontal, but between the two segments. We have to do that. Okay, where did I keep my? So actual rotation which is occurring is 2 theta. Is this clear? Not theta.
So will it be same to simply supported beam as well?
Sorry.
Simply supported beam as well?
Simply supported beam as well. This is simply supported beam.
Means if suppose more than two load is given, like then theta will be same.
More than 2 loads means you mean that we have a simply supported beams. It is subjected to multiple loads and then multiple plastic hinges are forming here. That's what your question is. Okay, so here also the rotation you will calculate like this. This is the rotation which is happening. Not from the horizontal. So by chance here this is horizontal. Let me take another case. So the deformed shape will be. So what is the plastic rotation occurring? Plastic rotation occurring is this and this. Okay. So in this case, where the load is acting symmetrically at the center, both sides are deforming by the same amount. Both sides, the angle is same. That's why I have written it as 2 theta, or here we are using theta p by 2. So you have to look at the configuration, then decide. Do not use the formula blindly. Okay, you have to think what is it. So this we can get as delta y plus phi p LP by 2 LP.
Sir, that will be clear.
Yes. Now his question. That what will be LP here? What is this LP? Here you can see that the steel is yielding on both the sides. It's not yielding only on one side. It is yielding on both the sides. Whereas in cantilever,
It is yielding to one side.
it was yielding only on one side. So LP here should be double. Okay. Same. Why same? If you say same, give the reason why you think it should be same.
We are making two cantilevers. So we are distributing the load into
Right, Q by 2 on both sides.
that is why sir it will be more than
But it doesn't depend on the load. It depends upon what length of the steel is going to be. So actually, this thing, what you are seeing here, in case of a simply supported beam subjected to central load, it happens in case of cantilever also. Why? Because practically you can't have a cantilever when we were doing testing. How we are doing testing? You go to our lab and see, we fix this foundation to strong floor, apply a load vertically or may not apply a load vertically, and then we apply Q, and the reinforcement we are putting here, it is going inside. The reinforcement going from here, it is going inside. You can't stop reinforcement exactly at the support. If it is a beam column, say, then also this reinforcement will go inside. You can't stop it at the face. Now what will happen? When the bending moment here is maximum, this has developed Fy here. Okay, and the corresponding strain is epsilon 1. So will this come to equilibrium at this point itself? What is going to happen inside the steel? If Fy is on this side, the Fy will be downward also. Okay? Now, this Fy, which is, or the stress which is Fy here, this will be registered by bond, and slowly it will become 0. You get it? So the stress distribution here, how the stress is varying in steel if I plot. So the stress distribution in the steel here will be like this. It is proportional to, let us say, bending moment. Okay, or maybe parabolic. Okay, so the distribution of the stress is like this. Here it is becoming Fy. What is happening here? Here also it is reducing to 0, slowly, gradually. It will not become 0 immediately. Okay, it will take some length in the concrete to transfer the stress from steel to surrounding concrete. Agree? Is it clear up till this point? Then what will happen? The strain increases further, more than epsilon y. What is going to happen? Suppose the steel is having some strain hardening. So stress can increase even further, more than Fy if strain hardening is there. So if the stress is exceeding on this side, the stress will exceed on this side also. Okay? And there will be elongation in steel. That elongation is going to be more than the elongation of concrete. So what will happen? Part of this steel here, this portion of the steel here, this will slip. The bond will get detached because steel is moving more, concrete is moving less. Okay. Of course, this concrete cannot crack because this foundation is so much. Here the concrete can crack. Cracks can go. But this concrete is not going to crack. It's foundation, large concrete. Or if it is in column, then this is also not going to crack. So what is going to happen? There will be debonding between steel and concrete. And it is cyclic. It will come, and when next cycle will come. When next cycle comes, what will be the distribution of stress? Can you tell me? If some portion of steel has already got detached from the concrete and next cycle comes. Can you plot the stress distribution in steel? What is going to happen? What will happen in that portion which has been detached?
Stress will be more there. Stress will be more there.
Why?
Because
It can't be more than what you are developing here. Equilibrium, so maximum will be this much only. It can't be more than that. It can't increase. It is going to either remain constant or reduce. So in this portion where the detachment has already occurred, the stress will remain constant. And transfer to concrete will take place only in this portion. You agree? Visualize what is happening at that interface. Okay, so you can think it like this. I will use your copy again. So let us say this side is our beam, and here is the column in which it is connected. So you are getting maximum stress here. Okay, and this portion is not connected, this is detached, and beyond that it is connected with concrete. So what will happen? Whatever stress is here, the same stress will continue, because this is like a free rod, and when it is in contact of concrete, this stress is going to reduce hugely, and some more portion here will get detached in the next cycle. So this length will go on increasing, and this phenomena is called yield penetration. The steel inside the support goes on yielding further and further. Okay, and this length in which this yielding takes place, we call this as LSP, the length of strain penetration or yield penetration, LSP. I have given you a very simple formula. मेरा कुछ कागज तो नहीं है जहाँ मैंने लिखा था वो गायब हो गया. किसी के पास वो है Priestley's book? You can open Priestley's book. So there is a formula there. In Priestley's book, which gives this LP as LSP plus some constant K times LC, and it should be greater than 2 times LC. Okay, because in a beam column joint what is happening? The same phenomena is occurring both sides. Okay, so 2 times LSP minimum, that much will be the plastic length. And what is LC? LSP I have already explained. This LC is the length up to point of contraction. Okay, K naught, this K or K naught this formula was written on that paper. I have forgotten. I don't remember. You can look in Priestley's book. Okay. And approximately it is equal to d by 2. Approximately. So earlier I have given you LP is equal to d by 2. That is approximate. This is more accurate empirical formula. Empirically it has been worked. Okay. So this length up to critical point of counterflexion. So in case of a double curvature beam, LC will be L by 2. Okay. And for LSP will depend on the ratio of ultimate strain, okay, to yield strain. How much strain hardening is occurring? I told you that penetration of strain depends upon strain hardening. So it depends on how much is the ratio of ultimate stress, to yield stress in concrete. How much strain hardening is taking place. Okay, expression is given in Priestley's book. You can take from it. Similarly, K naught.
Simply supported, it is simply L.
So in case of simply supported also, it is same. Because same phenomena is happening actually in all cases. What we noticed here, that it is happening, intentionally I have taken that example of simply supported to explain you that you understand that it is occurring on both sides.
Yes.
But it is occurring both sides not only in simply supported, rather in all cases. You can see here it is happening, it will happen here also. Because there will be strain, maximum strain is going to occur here and then it will reduce. So strain penetration is occurring on both the sides. In all the cases.
I'm asking about the LC. What is the length of LC you said, but it is the length up to the point of conflict.
Right.
So in the case of simply supported.
In case of simply supported, this will be L by 2. Point of counterflexion is where? 0 at the support.
Yes.
So support is point of counterflexion and distance of the point of counterflexion from the critical section. Critical section is the one where the hinge formation is taking place. Okay. So for example, in this case, this is the critical section. So from here to point of counterflexion, this is LC. Okay. Here, this is LC. And in simply supported case, this is LC.
One more concept.
Yes.
You told us that the length is detaching with the concrete. The length of
Steel
is
steel
detaching.
bars that detached from the concrete.
So I have doubt in this word detach. Means what is it? What is happening? Means it is losing. Is it losing? its
Bond
contact?
failure.
Bond
takes
failure.
place. So
Or
it is
plastifying.
It is plastifying also, and that's why the bond failure is taking place. So it is as if you have casted the original concrete, original steel with a sleeve, like in pre-stressing cables you are doing. Pre-stressing cables you are putting in a sleeve. Okay. So same way, this steel rod is put inside a sleeve, so that the bond between the concrete and the steel is not happening, is not taking place. Same thing, similar effect happens here when the steel elongates too much as compared to the concrete. So bond get failed. There is no bond remaining. Okay? So that portion, that is small length of the steel, that gets detached from the concrete. Okay? And this phenomena will happen again and again. Every cycle, this phenomena will happen. So, if you look in ACI 318, our code has very simple requirement here that this length is LD plus tan phi. That is the requirement in our code. If you look in ACI 318, it has a standard hook or standard what they are calling 90-degree band. Okay, so there this length is also fixed, minimum length is fixed. Okay, and this 90-degree band is necessary. Suppose you decide to give this straight LD plus tan phi. it is not acceptable. A hook has to be there. Why? Because slowly whole of this length will get detached under cyclic load. And then only this hook, mechanically, it will hold the steel from slipping. So this hook has a very important role, and this length should be sufficient so that in successive cycles, number of cycles which we are expecting during earthquake, it is long enough so that the strain penetration does not reach there. The yield penetration does not reach at the hook. Okay. So look at the detailing in ACI 318 for the beam column joint and compare it what is given in IS 13920. There is difference. There.
Why is the slip happening on this side? Like the
Both sides. This side I have explained. Actually, it will happen this side also. That's why I took the example of simply supported beam. So where this yield penetration will happen in both the sides. But this side, the length is so large, so that's not an issue. Problem is this side. Okay. So near the plastic hinge, the separation will take place, and in successive cycles, this length of the detachment, this is going to increase. So when we are defining plastic hinge length, it takes into account all these things. So when we have defined plastic hinge length, in this case, actually it takes into account LSP at the top and LSP at the bottom, and that's why that's why I have written that it has to be at least equal to 2 times 7. Because LSP both sides. So at least that much length will get plastic. Yes.
So sir, in practical cases, if we have a column and we have beam on both the sides, so for one beam we have to bring the reinforcement and we have to put it in the column, and from here also we have to do the same.
No. I am talking about the exterior joint. Interior joint, what we are doing? So at interior joint, this reinforcement is continued. This reinforcement is continued. So strain penetration will take place here and here. Okay. Suppose this full length that detached. What is going to happen? But stirrups are not connected to steel. Okay. It can't just slip because here and here it is connected. So slip will not happen. Okay. But you know, if this side is the moment, here it is moment is like this. So if it is tension this side, there will be compression this side. So what will happen? This steel inside will start slipping in the joint. So to avoid that should not happen. We take this as minimum 20 times diameter. Okay. So it should be minimum 20 times dia so that the strain penetration from both the sides should not join. This should not slip inside. And you can see it will also depends upon the number of cycles. So large number of cycles, more strain penetration will happen. Long duration earthquake, more strain penetration will happen.
Sir,
Yes.
interface here.
Yes.
First, plastic strain will occur or first bond failure will occur?
So it will depend upon how much is the bond strength which we have provided. So normally we provide bond design we do in such a way that before slip of the rod yielding should occur. Okay. So the design for bond is such, we calculate this LT length in such a way that the stress which we are getting there, okay, it should be within the limit of bond strength. Okay. So yielding will occur first, but once yielding occurs, then in some portion the steel will elongate, and that elongation is going to be more than elongation of concrete, and that's why the detachment will occur.
That elongation is taking on the outer side of the base.
Both sides, because stress has to be in equilibrium. So when you are considering this case, the stress is, let us say here, like this, let us say. So the stress here cannot be just like this. The stress here will also be like this. So if stress is like this, and this is increasing beyond Fy, okay, Fu is higher than Fy, it is increasing beyond that. So yielding will occur here, in this length, finite length, the yielding is going to occur. Suppose the steel does not have any strain hardening, then what is going to happen? Steel behavior is like this. Then what is going to happen?
Necking started that interface.
Yeah, nothing will start. So what is going to happen here when we have put this in our RCC map? As soon as here it will reach Fy. Okay, it will fail. The strain in that small length will reach ultimate. Okay, so there will not be a length of the steel which will be yielding. As soon as the steel at that point will reach Fy, okay, it will rupture. That's why this is very important that the strain should be, behavior should be like this. This should be high. And you recall IS 1390 in the beginning when we were talking about detailing? It gives a minimum ratio here that has to be satisfied. Because if this ratio is not there, plastic hinge length will be 0. Okay, we will not get any plastic rotation. We will not get any plastic displacement. Okay, and that's why in this formula also, this LSP, this depends upon the ratio of Fu to Fy. So this ratio is very important. That ratio decides how much will be LSP, and LSP is directly contributing to the plastic impact. So this ratio is important, and that's why in IS 13920 the minimum ratio is specified. Fu has to be at least, if I do not remember correctly, 15%. 1.1. 15%
So
higher.
it is saying at least it should be 1.15.
Right. So there is no upper limit.
Okay.
Okay. Minimum so much strain hardening should be there, so that when Fy is it is going beyond Fy here, so somewhere here it will be Fy. Okay, and whole of this length between Fy to Fu, this length is going to yield, and this length in successive cycles will go on increasing due to strain penetration. So are you able to visualize what actually is happening there? at the junction or at the center of, same thing will happen at the center of simply supported beam where hinge is forming, both sides. At the center first it will reach Fy. Suppose there was no strain hardening, then just at that zero line the strain will go on increasing and it will collapse. Okay, so strain will increase from epsilon y to epsilon u, okay, but there is no length in which it is occurring. So our LP will be changed. There will be strain ductility, but we will not get rotation ductility. Okay. Yes.
So this is the reason why load is not on higher size because it's
Why the load is not allowing?
we have to actually high
No, strain hardening, I am not sure whether it is there or not, but those do not have any epsilon u itself, because up till where it will go? Up to epsilon u. And if you see the stress strain diagrams of pre-stressing tandems, it is like this. So you may call that there is strain hardening, or you may not call there is strain hardening, okay, but whatever yield point you define here, the difference between epsilon y and epsilon u itself is very small. So as soon as yielding will occur, soon it is going to break. Although yielding will occur at much higher stress. That is another story, that the strength will be much higher, but ductility will not. So because of this reason, the code is saying that any steel which is having this elongation less than 14.5% shall not be used.
So,
Yes.
in case of steel structure,
Hmm.
the length of yield plateau that we get, that is limited to epsilon 6 times of epsilon y.
Steel structure you mean? So which I have plotted here. So you are talking about this,
This length
yeah, this plateau, strain plateau.
is
Yeah.
should not be less than 6 times of epsilon y.
Okay.
Why that limitation comes?
It is so that you get sufficient plastic strength.
Sufficient plastic strength.
Right. Because this is part of this total strain. No? This total strain depends on this and this. Okay. So total strain will depend on this as well as this strain. So this minimum value is specified in the code. Any other doubt? Can we move forward? Yes. Same. 2 times of LSP, or what we are obtaining from this formula. So minimum 2 times LSP or this, whichever is larger. Okay.
Sir,
Yes.
we have PLP both side. That question. We are cutting the simply supported at mid because both.
We are not considering cutting it. We are considering it to be consisting of 2 parts, and those 2 parts are fixed at the center.
We are considering that because behavior of both sides will be like a similar, like a mirror image. Okay.
Those will mirror.
Mirror image.
Yes.
If one side there is, if we are considering one part as cantilever, then this part will be supporting from this, like here foundation
Right.
and one.
Right.
If this part is like, then this part will be supporting like
Now
this.
you can think it like this: one part you have held up, another part you have bent up.
Ha. Then symmetry is not available there. Like here LP by 2 is for.
Now in this case symmetry will not occur when you have held it, and you are, in this case symmetry is not there, but actually what we are doing, we are applying this load like this. So this part is also bending in the same manner as this part is bending.
And sir, if the loading case is not symmetric,
Sorry?
Loading case is not symmetric.
Loading case is not symmetric.
If that
Okay.
concentrated load is placed at 2L/3 or something else
Yes.
other than the L/2,
Yes, that also. I
then we
have
cannot
considered.
divide by theta b/2.
Then this will be theta. This will be theta. This will be theta. This will be. So how you are measuring theta p? That's what I am explaining. So theta will be measured like this. The change in the slope between the two segments. That is our theta. That is our slope.
Now in this case,
Hmm.
if I have to find out deflection under that any one point load,
Uh-huh.
then again I have to cut it at that center.
No, that thing will not work here.
That will not
That will not work here.
because bending load
Here you have to assume the plastic hinges here, you have to perform analysis, gradual analysis and see. Okay. So only in case of a symmetrically placed load, I can consider the two parts as symmetric. If the load is placed asymmetrically, then this is not going to work. This technique, this method will not work here. Okay. Now let's extend this to further. Now you understand how to get the behavior of a fixed beam, a simply supported beam, a cantilever. Let us make this slightly more realistic. Okay, and let us consider a portal frame which is having rigid beam, rigid and strong beam. This beam is infinitely rigid and infinitely strong.
So I want to know,
Yeah.
please go to that synthesis model. Synthesis. It is in previous. This is.
Yeah.
So our question was, what will be the length of LP? So this whole length will be the LP.
Not whole length. First of all, I told you that LP is not the length which is yielding. I told you this, I made you clear in the beginning that LP is not the length which is yielding. Okay. LP depends on the length which is yielding, but it is not same. So what is LP? LP is a notional length which we are obtaining by equating the displacement. It depends on LSP, it depends on the length in which yielding is occurring, but it is obtained empirically in such a way that the displacement calculated like this, which we have done here, and what we are getting from
No, sir, what was in the corner? Slide number 2. Left corner.
Okay. So what was your question? Can you repeat?
Sir, the length of plastic.
Length of plastic. So length of plastic hinge is obtained experimentally, empirically from experiment, such that the displacement which we are calculating using this, okay, is same as we are getting from experiment. Okay. That's why this method we call phenomenological modeling, dumped plasticity. LP is not obtained numerically or analytically. It is obtained empirically. It is defined empirically. Okay. There are other methods also. Alternatively, what you can do, you can make a finite element model of this whole joint. Model your concrete also with small elements. Model the steel also with small elements, and study its behavior. When you apply load, steel will accordingly go on yielding. But you have to model the bonding also, because then only you will be able to consider the strain penetration. Okay. Suppose you do not model the bond, you assume perfect bond. Okay. Then you will not get the correct answer.
I got that, but the thing is, we considered the cantilever hypothesis. So in this case, you told us that the theta should be 2 times of theta b.
Right.
Okay. So in that case, we considered it like.
What you are looking for?
So means you are saying that the plastic hinge rotation theta b, it is 2 times of that. Means whatever we are considering
Right.
about the cantilever.
Right.
So if we are assuming that, or we are considering this hypothesis, so what, if we will not go into this empirical formula, then what will be the length if we will not consider this?
I was trying to tell you that only, that actually the phenomena which is occurring here
Yes.
is very similar. That's why all this discussion we did. I started from simply supported and then we came to this. So first I explained you simply supported, it is occurring both sides. And then I was explaining that both side phenomena is occurring even here. This is also same.
Okay.
So the simply supported or cantilever or frame, all are same. And the same plastic in length you can use in all the cases. That was the point I was trying. There may be slight difference, but on an average, you can use the same plastic in length in all the cases. Okay, so this is the assumption based on which our further study will continue. So the plastic in length formula, which is given in Priestley's book, okay, or roughly d by 2, we will continue to use for all structures, whether it is simply supported beam, it is cantilever, it is frame.
Yes.
Because phenomena is very similar. What is happening here and what is happening in the simply supported beam on both yielding of steel on both the sides, that occurs not only there, it occurs here also. Okay.
Yes.
So let's go to this problem. This hypothetical building where the beam is infinitely rigid. It is hypothetical. No real building will be like that, where beam will be infinitely rigid. But let's use it one step towards going to the real building. Okay. And here my columns are going to be formed. This is the displacement delta under this cube. Okay. Can you plot? Let us say this length is also L, this length is also L, it is EI here, it is EI here, but let us say the moment capacity is different. Here the moment capacity I am providing M, here let us say I am providing capacity 2M, here I am providing a capacity of 3M, and here I am providing a capacity of 4M. Let us say this is the situation. If you want, you can consider this also as 2EI, because here the moment capacity has increased. So if the moment capacity has increased, EI will not remain same. EI is also going to change. Okay. So let us say I have this type of situation, two columns. Columns are having different sizes and reinforcement. So their moment capacity is different, their EI is different. Okay. And moment capacity is like this, but these are connected with the rigid beam. And I want to plot Q versus delta for this hypothetical structure, where I am assuming the beams to be infinitely rigid. Can you plot? Let us say mu theta is equal to 4. So what is mu theta? Theta u plus theta 1. That is it. Then what comes to your mind if you have to plot this? Initially our structure is going to be elastic, at least that much you know, and how to get deformation of elastic structure under given load. Can you calculate? Please do that. Initially, the structure is linear elastic. So this relationship is going to be linear. Can you plot this relationship? Can you tell me what is going to be the slope of this line? What will be the relationship between Q and delta in the linear condition? We have to consider equilibrium, compatibility, and constitutive law. In case of linear elastic system, what is the constitutive law? जोर से बोलो, सुनाई नहीं पता. Stress proportional to strain. Okay, and if stress is proportional to strain, okay, what you will get? There is a relationship between EI, Q, and displacement. In linear system, we have done that. You can use that. For linear system, we have already calculated in the beginning, if you recall, the relationship between displacement, load, and EI. So using that, can you calculate? Under any given Q, what is delta? Is it a determinate structure or indeterminate structure? Indeterminate? Pakka? Anybody having confusion? Determinate or indeterminate? Indeterminate. How will you solve indeterminate structure? Yes? Compatibility equation. So you have to use some compatibility equation. What is the compatibility condition here? Both the columns are deforming by same delta. That is the compatibility condition. You will use that to solve it. So let us say it is subjected to this force Q is distributed as Q1 and Q2. Okay, so Q is Q1 plus Q2. And what is the relationship between Q1 and delta? Q1 is for linear structure. And Q2 so Q is, and here EI is 2 times, no? So it will be 24. Okay, so Q will be 12 plus 24, 36 EI by NQ delta. Agreed? How we have used compatibility to solve an indeterminate structure. Okay, you can also calculate the ratio of Q1 and Q2. So you can say that Q1 is 1 by 3Q and Q2 is 2y. Agreed? So how much is this ratio? This is stiffness. Q by delta.
36.
Till when this will continue? Yes, till when it will continue?
Till the moment in the left side column at the bottom.
Why left side column? Why not right side column?
So the weakest, lowest moment carried.
Lowest moment carrying capacity. But the moment occurring is also less. It is only 12 here. How much will be the moment here? Q1 into L by 2, and here it will be Q2 into L by 2. So the moment is also less. So how can you say this is going to yield first? So which point will yield first? How you will determine? That you can determine by using what we call demand to capacity ratio. Where the demand to capacity ratio will be maximum, there the first unit. Okay, so let me number these points as 1, 2, 3, 4. Can you calculate the demand? In terms of Q, how much is the demand at M1, M2, M3, and M4? Can you calculate these moments? You know Q1 and Q2, which are actually the two columns differently. Okay.
For location of M2 we have considered.
Sorry.
This M1 is at here bottom.
Right.
M plus.
Here I have written 1, 2, 3, 4. No? These are the M1, M2, M3, M4 are the moments which are occurring at these locations. The demand at these locations. Okay. So you can see that the demand at 1 and 2 is same, and demand at 3 and 4 is same. So M1 is going to be M2, M3 is going to be M4. But how much? M1 will be in terms of Q, isn't it? Or in terms of delta. You can calculate M1 in terms of Q or in terms of delta. Applied force is Q, so it is better to calculate in terms of Q. M1 is 12 by 6. How? How it is 12 by 6? Can anybody explain? See, it is like this. this displacement is delta. The force here is Q1. We are calculating these moments. Okay, you can consider this as the point of counterflexure. So, okay, so how much is this moment? Here the moment is 0. So this is Q1 into this length, which is same as Q1 into this length. How much was Q1? Q by 3. So Q by 3 into L by 2. So QL by 6. How much is M3 and M4? Sorry? QL by 3. QL by 3 and QL by 3.
Moment we have to calculate at bottom of this now.
At bottom as well as
That will be Q1 into circle L, Q into L.
you make a free body diagram, then you will understand. You can also make the free body diagram of the whole system. So here is Q1, here is Q1. There is a moment here and here, both. Both are equal. So how much is this moment? You take moment about this. How much will be this moment? This will be Q1 into L, or rather 2m will be equal to Q1 into L. So from here also you will get m is equal to Q1 L by 2.
Why we are going with the duplicate shape?
No, do not deflect. If you are not happy with the deflected shape, I have no problem. You consider this. That I was showing only to show you the direction of this. So if you are not happy with this, consider this. So it will be same. So everybody is clear up to this point? So next step, we will calculate DCR. DCR at point 1, DCR at point 2, DCR at point 3, and DCR at point 4. What is DCR at point 1? The demand QL by 6 divided by capacity. Capacity at 1 is M. Okay, DCR 2, 6, 2M. At 3, QL by 3 and 3M. So 9M. And QL by 3 divided by 4M. So 12. Okay, so where the first plastic hinge is going to form, where the capacity will be exceeded first. Everything is linear, everything will go on increasing in the same proportion. Okay, somewhere the capacity will get exceeded first. Where it is going to be exceeded first? At point 1. Okay, so DCR max is equal to DCR 1, and let us equate this equal to 0, sorry 1. When we equate it equal to 1, what does that mean? That the demand is exactly equal to the capacity. That means the first plastic hinge is occurring here. And if we do that, then we get Q as 6m by L. And what is corresponding delta? Where the first hinge is occurring, let me call it Q1, corresponding to the first hinge, and the corresponding delta 1. Till this point, our system is linear. So whatever relationship we have obtained in the beginning, same relationship is valid. So using that relationship, how much is delta 1? We have calculated the slope. So 36 EI by L cube was the ratio. Okay. So how much will be delta 1? ml square by 6. So we have got our first point. Q1 we have obtained as ml by 6, sorry, and the corresponding delta 1. Okay, now what? Has our structure failed? So, how our structure will look like at this stage? Here we have developed the plastic. Okay, so let us do an incremental analysis beyond this. When the hinge has formed, other points are still intact, so it can still deform. Okay, it can still resist load. Let us say that load is Q2. Okay. Now, there will be some displacement in the same manner as we have done earlier. Let us say this displacement is delta 2. Can you calculate the relationship between Q2 and delta 2? Sorry? 6 CI. 6 CI is what? Right. 6 CI. Okay. So how did you got this 6 CI? What is the stiffness? Plot the deformed shape first. How the columns are going to deform now. From there we will get the shape. We are considering only the incremental deformation. Previous deformation, whatever has happened. We are not considering that. The displacement, if you have a structure in which one point is hinged, released, then how it is going to deform? That you have to plot. And then you can calculate the relationship between Q2 and delta 2.
Previous information plus theta.
It is hinge here.
Hinge here.
So at hinge, how much is the moment?
This will be plastic hinge, na?
Plastic hinge.
Ah.
But that the plastic hinge consists of two parts. I told you that it is like a rusted hinge. So initially it will take load and then it will not take load. Okay. So that portion in which it was taking load, this we have already consumed. So now there is no more capacity to take load. It will be as if it is free to rotate. It is like a release. Okay. We are doing, you have to keep in mind, we are doing incremental analysis. Beyond this point, what is that? So still, this structure can be considered as a linear elastic structure with one release here. And then the deform shape will be here, of course, it is still going to deform like this because still both ends are intact. But here what will happen? It will deform like this. Here the compatibility will be satisfied, this angle will remain 90 degree. Here, zero moment. So there will not be any curvature. So it will deform like a cantilever, inverted cantilever. Let us say this force is Q12, this is Q2. Write down Q12 and Q22 in terms of delta 2. So Q2 is 24 EI by LQ delta 2. 27, not 24. Everybody please check whether this is correct. You do it yourself. In case of a cantilever, how much is the displacement? Do you remember? Cantilever. This is cantilever. How much is it? Just now we said something. 3 EI by L. Yes. So here relationship between Q1 and delta 1 will be okay, and Q22 what is the relationship for fixed? We have used earlier also. Okay, so you add Q1 and Q2. Sorry, not 12.
12 into 2.
2 EI also. Yes. So it is 24. So Q2 will be Q12 plus Q2. You can calculate Q2 in terms of delta. Keep in mind it is not square. Huh? I am talking about second iteration. So it will be better if I write it like this in bracket. That will also be. That is also a notation which we use for second increment. So this superscript 2 is representing second increment. So now this curve will be like this or this curve will be like this. The slope has increased or slope has decreased. Earlier it was 36. Yeah. Now it is 27. So slope has decreased. Means the structure has become flexible. That is obvious. If one point you have released, it will become flexible. Till when it will continue? This curve, till when it will continue? When? The second hinge. And where will the second hinge occur? How do you know that it will occur at 2?
Third.
3 or 4? How do you know? Same thing you have to do. So you have to calculate demand to capacity. But keep in mind, now the capacity you have considered is the residual capacity. Because out of that total capacity, some capacity has been already consumed in stage 1. Here, when this was occurring, some moment was already there. Okay. So that moment, we are doing incremental analysis. That moment you have to subtract from that capacity. So you have to calculate remaining capacity first. So calculate the remaining capacity here. How we are going to calculate remaining capacity? When Q1 was 6 M by L, how much was M1 in the first iteration, M2 in the first iteration, or first iteration, first increment, and 3 in the first increment, and M4 in the first increment. Can you calculate? When Q is 6 M by L, we have already calculated M1, M2, M3 in terms of Q, QL by 6. So 6 here, it is 6 M by L, and M we can substitute. So M1 is QL by 6 and Q is 6 M by L. So how much will be that? M1 will be equal to M. Okay, and M2, M3, M4. So the residual capacity will be how much? This minus the capacity. Okay, M3, capacity minus this. So at 1, how much was the original capacity? M. Out of that, M is consumed. It's 0. That's why there is plastic. In the second case, M2, 2M. Out of 2M, M is consumed. So remaining is remaining capacity here is M. Similarly here, there was 3M. Are you clear about this? This will be the moment in our frame when Q1 is reached. Okay, so when this Q1 is reached, this will be the moment. Original capacity is M here, 2M here, 3M here, 4M here. So from this, we have to subtract what demand was there at the end of phase 1, end of increment 1. Whatever demand was there, that we are subtracting, so that we know how much is the remaining capacity. Because our analysis we are doing beyond, in increment from here. So till this point, some movement has already occurred. So total capacity was, let us say, 2m. Out of that, m has already occurred. So remaining moment which is there to resist the forces in this second case is only m. Okay, so that balance capacity is 0 here. It is m here. How much is here? 2m. Original was 3m. How much was the demand at the end of first phase? 2m. So remaining will be m. And how much is here? 2m. So now you can calculate a new DCR. Okay, you have calculated Q. You calculate new capacity first. Sorry, new demand first. Capacity you have calculated. So M1 into M2 into M3 into M4. This is of course G. This was hinge. So no new moment has come. So how much is M2?
At first stage, our demand is up to m.
Right.
At the end of the first stage,
Right.
then we are calculating this one.
Right. But at the same time, the demand here and here and here we have to calculate.
This we have calculated in second stage.
Right.
Then we are considering the second stage. Here will be 0, here will be m, here will be 2m, here will be 3m.
Right.
Why you are putting here 1m now?
No, because here the demand is 2m. This is 2ei now. So when delta was occurring, it was m here, it was 2m here.
Okay, due to this 2a.
Due to this ei, higher ei. So you can check that here it was 2m actually, double. So when it was occurring m here it is occurring 2m. That's why I have subtracted 2m from it. Yes. Which one? This is consumed. This is consumed. This is what is occurring there. Okay. This we have calculated what is occurring there at the end of first increment. And difference of this from the original capacity will give us the residual capacity. So residual capacity after at the end of step 1 or in the beginning of step 2. That is we have obtained. Now let us calculate the demand in step 2 in terms of Q2. Yes? 9 MI. It will be in terms of Q2. Q2. Let us calculate in terms of Q2. So when the load here is Q2, how much movement is going to occur here, here and here? That's what we are calculating. So Q2 is still unknown. We don't know how much is Q2. So let us calculate this demand in terms of Q2 first. Then we will calculate DCR and the maximum DCR we will equate equal to 1 to get Q2. So during increment 2, the applied load is Q2, and due to that moment will occur at different locations which will be in terms of Q2. That moment we are trying to calculate. The demand or the moment occurring at different points under step 2, increment 2. You have to consider the deformed shape for calculating that. We have already calculated Q1 and Q2 in terms of Q. You can calculate now Q1 in terms of Q12 in terms of Q2 is how much? Relationship ratio between Q1 and Q2 is how much?
1/9.
So it is 1:8. Okay. So Q1, or let me say Q22 is 8 times Q12.
9 times.
8 times. Q1 and Q2 is 3 and this is 24.
This is Q22.
Right. So I have also written Q22 on this. Q22 is, so you are one step ahead. So Q12 will be in terms of Q2 how much? Okay, and then you can write down M22 in terms of Q12. How much is M12 in terms of Q12?
Q1
This is our M22. How much it is in terms of Q12?
Q12 times L.
Q12 times L. So that means, and Q12 is 1/9Q. So this is QL by 9. Q. Yes, you are right. M3 similarly. M3
Q2 times L/2. So
Q22 times L by 2. So that is 8/9 times Q2 L by 2. So that will be 4 Q2 L by 9 and 4 Q2 L by 9. Agree? Take your own time. No hurry. But everybody should be clear. If you are not following any step, ask me. Yes. This is demand. Okay, I'm sorry, I have forgotten to write what we are writing here. Okay, so this I am writing demand in step 2. Okay, so this is demand in step we are calculating, and this was demand at the end of step 1. Okay, and this is here what I have written here. This is remaining capacity. At the beginning of step 1. Sorry, beginning of step. End of step 1 or beginning of step 2. Okay. So now can you continue like this? You will take the maximum DCI, yes? साहब बोलो ऊपर कर दो. Yeah, it is towards pushover. Something similar we do in pushover. Okay. In fact, what we have done for cantilever, that was also pushover analysis. So we have started from pushover analysis of simplest structure, that was cantilever. Then we moved to more complex structure, which was either simply supported beam or fixed column or beam. Then we moved to further complex, where the beam is infinitely rigid, but still it is not real beam, real structure. Real structure is a frame where beams and columns both have finite strength and stiffness, not infinite. But we are going step by step in that direction. At the end, we will reach it. Okay? So, let me take the attendance. Please continue this. We will continue when we meet tomorrow. Tomorrow we are meeting at 12. So when we are meeting at 12, we will continue from here. Take your own time. Be very clear about it. Okay? Any step you are not following, although it is simple. Only thing is that we are doing repeatedly. Otherwise, it is just what you have already learned. Anirudh, Abhishek,